Today we are talking about section 7.2, graphing equations by plotting points. A linear equation is an equation that contains only constants and variables that single variables that have an exponent of 1. So if you see an equation like y equals x squared plus x plus 1, that would not be a linear equation because we have an exponent greater than 1 in the equation. So just know that. Make sure you realize that the linear equation, the variable will have an exponent of 1. And you can see the word line in linear. So that should help you remember that when you graph a linear equation, you will get a line. And you need 2 points to graph a line. Any number, if you have a single point, any number of lines can go through a single point. But if you have 2 points, there's only 1 line that can go through those. So as an example, y equals 2x minus 1. We know that this is a linear equation. It has single variable terms, and the exponent on the variable is 1. And it also has constants. So to graph it, we would take a value for x and plug it in. So plugging 1 into this equation would be 2 times 1 minus 1 equals 2 minus 1 is 1. So we would graph that point right there, 1, 1. Then we could put in 2. 2 times 2 equals, or minus 1 equals 3. So we put in 2, our x value was 2, and our y value became 3. So we go over to 2 and up 3, and we get that point right there. Now we could go ahead and graph it, and would get pretty close, but the book is recommending that you do 3 points. 2 points are what's needed for the straight line, but the third point can help reduce errors. So let's put in a number on the negative side of the x-axis. Now let's put a -1 in. So 2 times a -1 minus 1 equals, well, 2 times -1 would be -2, minus 1 would be -3. So our x was -1, and our output, our y, was -3. So we go -1 on the x-axis, and -1, -2, -3 on the y. We get -1, -3, and that can help make sure that our line is accurate. If I just had those 2 dots, I might have gone something like this, or I might have gone something like that. But that third dot does help to reduce error. And so my graphed equation would look something like this. And graphing the equation is helpful because then you can get an idea of what the value for the function or the equation would be if you have all these different x values without having to actually do the math and find out that value. So graphing the equation can be very beneficial. All right, so to graph a line from its equation, Oh, I forgot to mention one thing real quick. You can take a point, like if they ask you, is 3, 1, is 3, 1 a valid point for this function, y equals 2x minus 1. To find that out, you would go y equals 2, well, my x value is 3, times 3 minus 1, and you'd get 6 minus 1 is 5. Y equals 5. But you get a y value of 1 here. So you know that this point will not be on that line. Sure enough, if you graph 3, 1, you'll see it's not on the line. All right, to graph a line from its equation, you want to set up a table of values first. 0, -1, and +1 are 3 very easy values to work with. So when you're trying to graph a function, you literally get to choose whatever values you want to put into that function. If you want to put in 1,000,000, have at it. But you're going to end up with some ridiculous graphing. So it's easier to go with some easy values, 0, -1, and 1. So then we would plug 3 x values into the equation. The x values in these examples are going to be our inputs. That's what we're putting into the function. And then what we get out of the function is the output. Also, if the thing that you're putting into the function is something you get to choose, it's not dependent on anything, then it's also the independent variable. So my inputs are my independent variables. My outputs depend on what the value of that independent variable is. So therefore they're called dependent variables. So let's look at this example. Y equals -2x plus 3. You just plug in the x, -2 times -1 plus 3. -2 times -1 is going to get you a positive number, a +2, plus 3 equals 5. So 5 is our first value. All right, now we're going to plug in 0. -2 times 0 plus 3. Well, anything times 0 is 0. Plus 3 is 3. So our output, our dependent variable, is 3. Now we're going to plug in 1. -2 times 1 plus 3. -2 times 1 is -2. Plus 3 is a +1. So we get 3 ordered pairs. -1, 5. I'm going to erase this. So we go -1, 1, 2, 3, 4, 5. Quick review. This is the Cartesian plane. This is the x-axis. This is the y-axis. The ordered pairs always come as x, y. You always go on your x-axis first and then adjust up or down for your y. So this would be -1, 5. Then we have 0, 3, 0. If the x-axis, if the x value is 0, that means we don't have to go left or right at all. You can just go up or down depending on what the y value is. Well, the y value is a +3, so I'm going to go up 1, 2, 3. And then you just want to make sure you're not leaving dots all over as you're counting. So now I have 2 points on my graph. And the last point is 1, 1. So I'm going to go positive 1 and then positive 1. And then you make your line. And I forgot to do this part. Add arrows. A line has arrows in either direction. So that is graphing y equals negative 2x plus 3. Now, I did just tell you that 0, negative 1, and 1 are the easiest values that you want to plug in. But sometimes it's a good idea to look at your problem that you're needing to solve. Because if I multiply negative 1 times 3/4, I'm going to get a fraction. And fractions are hard to graph on a graph like this. So remember, we get to pick whatever values we want for our x. So if I pick a 4, then my 4's will cancel out. So I'm going to go with 4, 0, and negative 4. 3/4 times 4 minus 2. These 4's cancel out, and I'm left with 3 minus 2, which equals 1. That's my first output, or dependent variable. If I plug negative 4 into it, I'm going to modify that to a negative 4. Excuse me. Oh, my negative 4. But I still have a negative 1. Don't forget about the negative 1 there. So here now I have negative 3 minus 2, which is negative 5. And then finally, I have 0. Well, anything times 0 is 0. Minus 2 is going to give me a negative 2. So then I come over here to graph, and I have 4, 1. So I go on the x-axis to a positive 4. 1, 2, 3, 4. And then I go to a positive 1 on the y-axis. So I'm going to go up to a positive 1. That gets me the point 4, 1. Now I'm going to stay at 0 on the x-axis, and I'm going to go down to a negative 2. 1, 2. And that gets me the point 0, negative 2. Remember, x is always put first in the ordered pair, and y is second. Then negative 4 and negative 5. I'm going to go on the x-axis to negative 4. And then on the y-axis to negative 5. 3, 4, 5. Negative 5. So I end up in quadrant 3 on that final point. And quadrant 1 had that first point that I had graphed. And then I'm going to attempt to connect these dots. And add the arrows to my line. And we have graphed this second linear function. All right, I think that's it. I had just skimmed over it, but remember, you can plug in. If it's asking you, does this ordered pair show up on the line, you have to plug the x value in and find out if you end up with the y value. So one more quick example of that. Let's say that we had this point right here. This would be a negative 3 and then negative 1. and we want to know whether or not that's a point of a valid point for this function, y equals negative 2x plus 3. We would find our x value, which is negative 3, go negative 2 times negative 3, which is a positive 6, and then plus 3, which gets me 9, except that my y value is negative 1. So this point would not be on that line. When you have the graph and you're looking at the graph, it's obvious. But when you only have the function and you're given a point and you need to know whether or not that point is on the graph, it's not so obvious. So that's how you figure it out. You plug the x value into the function and see if you get that y value out. If you get that y value out, it's on the line. If you don't get that y value out, it's not on the line. All right, good luck with your assignment.